Welcome to the dynamic learning hub of XLR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri Metro. In our journey of over a decade, we have proudly trained over 2 lakh students. We have also been recognized by Deloitte, Silicon India, and other accreditation bodies. Experience learning like never before in our spacious and comfortable classrooms. With high-definition projectors and state-of-the-art acoustics in place, we ensure effective learning even to the farthest point in the room. The hybrid mode is a game changer as you can enjoy the benefits of a live classroom from the comfort of your home. Even if you happen to miss any classroom session, you can still attend the same session with the same trainer at the same time at your convenience, maintaining consistency in your learning progress. Wanna get started? Join us for a demo or career chat over a cup of coffee at our Andheri branch. XLR. We don't just train, we build careers.
Yes, so the collaboration with XLR was an excellent one. We conducted a Power BI workshop with Advanced Excel over a span of 3 days. The workshop was almost 12 hours long in total. Mr. Karthik, who was an amazing trainer, helped the students understand the concepts deeply. I am sure that the students will be able to apply these concepts in their careers as well as their daily lives.
The trainer, Mr. Karthik, was an excellent person where he explained in very detailed manner on how to give great insights using very complex data sets.
Right, good evening everyone. Hope I'm audible and the screen sharing is also working. Can you confirm that with a yes in the chat box? Hope I'm audible and the screen sharing is also working. Right, good evening. So let's go with okay. So yesterday we have talked about trees. We have talked about the terminology. Today we will be going through the searching techniques in it. Okay. I know you guys are not familiar with normal tree etc and all, but yeah, this session is generally for DSA product based companies. So expecting you have basic knowledge of it, and we are not creating everything from scratch like creating a tree, inserting, deleting and all. Okay. Let's try to cover as much as possible and as much beginner friendly as possible so that you'll get an idea about how everything generally works here, and you will be also able to start your DSA journey with it. Okay. So yeah, 2 hours will not be sufficient for to cover any single topic. No? So that's what I wanted to convey. Anyway, now see, let's open lead code. let's go with let's go dark mode. Yeah, let's open lead code. Now what we'll do is we will go with the traversals. Okay, we'll say tree traversals. Okay, you see we have in order, we have pre-order, we have post order, etc. and all, right? Well, go through them. First, let me take you through what actually we do in a tree, and I hope I have shown you some presentation earlier. Just a second. Yeah, you see, coming to tree traversals, we have pre-order. As I said, pre means first we will be accessing, okay, we'll be accessing then we'll be accessing okay, the left subtree, then we will be accessing the right subtree. Now, post order means first you will be accessing the left subtree, then you will be accessing the right subtree. Internet connection is unstable. Right. What's happening? You guys are able to hear now? Yes. So, yeah, I'm at a weird place. So, you need to adjust one more day. Signal. Sometimes I'm getting good signal. Okay. So, yeah, now I hope it's fine. It's better. Yeah. If I'm at a new place, so that's fine. Anyway, a route. First route, then left, then right. Post means left, right route. A means left, route, right. That's how we will be accessing everything. Okay. Now see here, see this one. Coming to traversals, this is a tree. Okay, binary tree. We have, at most it will be having two nodes: pre-order, post-order, and in-order. You can see the after. Let us go how we will be able to access it. Okay, first pre-order means you will be accessing the root node. The root node is I have added. Then I need to move to the tree. Okay, first tree means root, then go to left, and here also you need to take the root node. And my one tip that I would like to share with you all is whenever you're dealing anything, okay, just consider the individual branch as the main branch. Like when you are this, you are accessing this one. So first you will be accessing node, then you will be accessing left subtree. Imagine this one as your created again, and this is going root. That's what I wanted you to imagine here. Everything is fine. Still any audio issues? Still any audio issues? Any audio issues? Okay, let me know if there are any. This one tip is, whenever you're trying to go through recursion, consider every individual tree as okay, the main tree. That's will be very easy for you. Root node, that means B we have accessed. Again, we need to move to left. Okay. Now, for this one, do we have any left branch? Do we have any left branch? No. Means you have accessed okay, the element there, that node, etc. and all are done. So left is completed, root is done, left is right. Do you have any right? No. So you will again go back. You see, for this one we have access to root node, we have access to left node. So root done, left done. Now you need to access right. Now for this one, this is the individual element, this is the root node. Okay, we don't have the left node and right node again. So that's how you will be accessing it. So let me delete all these things. Now consider pro tip, whenever you're going through recursion, consider every individual iteration as the main iteration. Or in this tree, if I'm accessing this particular subtree, think about it as the main tree. You see here, if I'm accessing this particular subtree, or if I'm accessing this particular subtree, think about it as it is the main tree. C is your root node, F is the tree, G is the right subtree, in that manner. Okay. Now see here, let's continue. Let's go move forward. So we'll be accessing the left subtree is completed. We'll come to the right. Now we will be accessing the root node, that is C. Then go to left subtree. Okay. We have access to the root node. We don't have a left thing, the right value again. Okay. So left done, right done, left is done, right is done. Everything is. So this is how we will be. Don't worry, we have two examples, you will understand it. Now coming to post order means, let's write here. Post order means the root will be accessed last. You see, first left, then right, the root. Okay, I'm present here. I have to go to left. Consider this as your main tree. Okay, you're present here. You need to go to left. You're present here. If I go to left, there is nothing. So I have accessed it. After left, I need to go to right. There is nothing. So I have accessed it. Left is done, right is done. So I have to access the root node. So first accessed value will be D. After D, you see left is completed. For which one? For B, left is completed. You need to access the right, and the same thing for this, left and right are done. So you will be accessing E. After D, you will have E. Then you will be having the root node. Okay, you see, first left, then right, then root. Consider this as your main tree. If you observe, if I delete all the drawings, okay, first D, E, B, then this is the left. Left is completed. Left is done. Now for right, you need to do the same. Okay. So can you tell me for right? Can you tell me for right what it will be? Can you tell me for right? Let me get started. First, we'll come to this pointer. We'll come to this pointer. Left, right, root. Okay. Left is done. Right is E. Then root. Okay. Left is done. Now coming to the right portion. So after D, E and B, what will be the next node? After D, E and B, what will be the next node? After D and B, what will be the next node? Okay, D, E and B, after B will be the next node. Hey, yeah, you see, the B is already present now. I'm asking what will be the next. Okay, no, not A. Not A. I hope you all are remembering this. This is post order. Post order means left, then right, then root. Okay, left, right, root. Left is done. This one, this is left, it is done. We have to go to right. So which one in right? Which one in right? Very good. You see, I'll come here. Again, left I need to move. Again, left I need to move. There is nothing here. For F, there is no left null. Then I need to access right. So G I'll access, then root, then F. Now for C, left is done. There is no node present in right. Then C. For A, left is done. Right is done. Then root. Okay. Now let's move over with this. Let's go ahead with this. Now see, B is completed. Now you will come here, G, left, right, root. For C, left is done, right is not present, so root. For A, left is completed, right is also completed, now root. Okay, so D, E, B, G, F, C we have. D, E, B, G, F, G, F, C, A. Now let's see last one. This is traversal. So what is the order of order? What will be order for in order? In order means left, then root, then right. Left, root, right. That's how we have to access. So first, where should you move? You have to move to left. Where should you move? You have to move left. Okay. Do we have any left for D? No. So left you have already accessed then. You see there is no left for D. Left is accessed. Then root you will access, that is D. Now do we have any right? No, right is accessed. Now you will come back to the previous step. Now you see for B, left is accessed. Okay. Then you will access the root node, means after B you will get B, after B you will get E. So left, right, root. Okay. Now after that again you have the left part, then root A, then the right part we need to do. Okay? It's gonna continue in that manner. Such that if it was an offline session, I would have shown you through hand gestures, etc. and all. Since it's online, this would help you a little bit. I want you to understand. It's pretty easy actually. Okay, it's pretty easy actually. Done. Now see, left is done, root, right, left is done, root. The leftmost node here, so we have the go, we don't have any left value for F. So root is accessed, then the right value. Okay, now everything is accessed here. We'll again go back. For C, left is done, so root, and we don't have any right, so it will simply end. So this is the order for it. Okay. First step, pre-order. You see, pre-order. First I have to access the root node. Then what will be the next node? Tell me the next node. After it, what will be the order? Which one? This is pre-order. Pre-order this is. I hope you can see the name. Pre-order means, what is the order? Root, then left, then right. Okay. First root node, then left node, then right node. So I have accessed A here. What will be the next node I have to access? What will be the next node I have to access? Hello? I hope I'm audible. Yeah. Now I'm getting your answers. So next node I have to access is very good, B. What after B? After B? After B? Very good. D. After D? After D? After D? Okay, some are saying C. C is the wrong answer. One more chance. C is the wrong answer. Okay. F you are saying, you see Yeah, sorry, I lost my connection there. Yeah. Yes, I lost my connection. Okay. Small internet issue. Please adjust one more day. Okay. Yes, so you see here we got D. After D, which one we will be getting? We'll be getting, I've explained this again. So see, pre-order means left, sorry, pre-order means root, left, right. Pre-order means root, left, right. So you have already accessed the root element. After that, try to go with left. Do we have left? No, no left. So you will come to the right. And what is the pro tip I have told you? Whenever you are trying to go with recursion, or whenever you are looking at this tree here, think about this subtree as the main tree. Okay, forget about all the other things. So here we have it. So here we will be accessing the root node, that is F. Then we will go to left, go to right. Okay, root left, right is the order for it. That's how everything will be accessed. Okay, now let me clear up and go through the presentation. We'll be able to see that order. Okay, now first F, then go to left, then go to right. Okay, now what will be the next, what will be the next node I have to access after F? Sorry, after I. What will be the next node after I? After I. No, not C again. You see, we are still in touch with this one only. This is the root node that you had. For it, left is completed, right is just completed. Okay. Now for this one, this root node, left is completed. We need to complete right. So we have to close this one. Then we will go through it. Okay. So first E, that's why I'm asking you at time to time. You have to be okay visualizing this, and you can see the color change as well. That will help you a bit. So for B, left part is done, D is done. Now E, for the B node A, left is done. We have to go to right. So again, right, we will be accessing, okay, it doesn't have any, so it doesn't have any end of root is accessed left and right. Okay, understood this one? Any doubt in this one? Pre-order is okay now. Pre-order order is okay. Yes, I understand. Yeah. Let me try to change my position. Maybe that will help us a bit. Just a second. Now it's fine. Now you guys are able to hear me. Now it's fine. Yes, so understood pre-order. Any doubt in this? We are closing pre-order. Understood pre-order? Clear? Or do you want me to explain anything again? Okay. Once you get a hang of it, once you follow my tip, what is the tip? Whenever you're be a very good thing. Okay. Recursion, generally we have to forget about the previous iteration. We have to just look at this one. For example, if I am accessing this particular tree here, I think we cannot move this one. I need a good, yeah, fine. Maybe we'll have it. Right. When you're trying to access this one, consider this as your main tree. Or when you are going with the left subtree, consider this as your main tree. Or when you're going with the right subtree, consider that as your main tree. That's how things will be easy for us. Okay. Done. Right. So pre-order is done. Now let's see the next one. That is post order. Can you please give me the entire post order? Can you please give me the entire post order of all the notes? Order of all the notes. And if I have to give you the, no, that's okay, but the answer here, if I give you post order means first left, then right, then root. Okay, I'll write it here. Give me the entire answer. Give me the entire answer. Give me the answer. Okay, we'll make it host and co-host only. Done. Give me the entire answer for post order traversal. Post order traversal, we'll discuss about it. Me to host and co-host. Yes, you can message me directly. Give me the entire answer for post order travel. The entire post order traversal. We got 4 answers, I guess. Yes. H I F D E B G C A. H I F D E B G C A. Okay, very good, very good. We are getting good responses. Maybe these quizzes are kind of like something that you guys are interested in to respond. Nice, 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 guys. Okay. So let's see. First, post order means we have to go to the extreme left. So you see, I am currently present at A. Does it have left? Yes. So move to left. Okay. I am currently present at B. Does it have left? Yes. Move to left. I am currently present at D. Does it have left? No. Then after left, what should you go? You have to go to the right direction. Okay. Does it have left? Yes. For H, does it have left? No. Does it have right? No. Then left, right are done. You have to access root. So first value will be H. Now when you come back, for F, left is done. Right is I. Node is F. For D, left is done. Left we don't have anything. Right is done. So root. For B, left, right, root. For A, left is done. Now coming to right, then left, right, root, etc. This is how it's gonna go with. Okay. I hope you guys are able to give the correct answers. Anyone got it wrong? I hope everyone gave the correct answer only. CGA. Yes. Perfect. Perfect. I think we can move forward. You guys are perfect in it. Done. Now see the next one, last one, in order. Tell me in order. Tell me in order traversal. Tell me in order traversal. I'll again make it to host and co-host. Okay. Tell me in order traversal, and I hope you remember. In order means first we'll be having left, then we will be having root, then we will be having right. This is in order traversal. HFIDBEAGC. Okay, very good. HFIDH. Okay, DHRT, you are coming up with D. Why? D means okay, left. Done. Correct only means the remaining people are giving me H. Let me show you. You see, first we are presented the root node. If you have left, go to left. If you have left, go to left. If you have left, no, left is access. So once left is accessed, which one do you have to access? You have to access root node only. Okay. So I got some wrong answers from Chitranj. Corrected. Aarti gave us correct. I was thinking, no, Kushi, you got it wrong, I guess. Amrita also wrong. Priyanshu also wrong. Now correct yourself, guys. I hope you understood this point. Any doubt in this point? Let's see, Bunny also got it wrong. Aditya, yes, Aditya is kind of in the right track. Okay, you got this one, understood this one. First go to extreme left. You see, we don't have any left part here now. If you don't have it, imagine that as null. You have accessed it. So left is completed, then root, then go to right. For this one, again left. For this one, left. Then left is completed, then root. So after D you will have H. After H you will have F. After F you will be having I. Left, root, right. Okay, you guys are correcting yourself. Correct it. Give me the correct answer this time. Take more time, no issues. Take more time, no issues. Give me the correct answer this time. Correct it. Correct yourself. Okay. Post it. Use the chat box. Use the chat box. Okay. Done. So after D, which one we will be having? After D, we will again come back to left. Okay. Left, root, right. Now for the B root node, if you observe, left is completed. So root is B, right is done. For the A root node, left is completed. Next the root node is A, then the right. Now coming to right side, for C, left is done. Left is done. So root is C itself, will go to right. Okay, this answer. Any doubt in it? Any doubt? Any doubt? Let me make the meeting group chat. Any doubt in it? Understood? This is clear. This is fine. This is okay. Should pre-order, post-order, traversals and all. Okay. Understood all this? Perfect. Let's go ahead and code it out. I told you yesterday to go through recursion once. Have you gone through recursion? Did you revise recursion? Did you revise recursion? Done. Let me open pre-order first, then post-order, then in order. Okay, I have all these three questions opened here. I'll solve them through recursion only, and I'll show you the visualization for one of them. The rest of them you should be able to do. Okay, so let me make it full screen. Binary tree pre-order traversal, given root of a binary tree. Binary tree means at most two nodes only you will be having, just the ones that you have been seeing so far. Okay, so return the pre-order traversal of its nodes. So they want us to return it as a list. You see, this is only for us to understand. Okay, and how they generally represent everything in the memory is, let me just write it down so that if there is anyone who is beginner, you will understand it. Let me make it white also. Let's say we have 10, we have 20, we have 30, we have 40. We doesn't have anything, so I'll just write it as null. We have 50. Okay, we have 60. In this manner, if you have it, if you don't have anything, that will be null. You can just imagine it's null. Null, 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 null. Okay, done. That's it. Now how they would write it is, first they will go with the root node. Okay, then the left node of it, then the right node of it. Okay, so you see here, for 1 we have, there is no left node, so it is null there. For 10 we have 20, and then we have 30. Then you will come to the left node value. Again, left node's left, that is 40, left node's right, that is nothing but null. This is how they generally write it. Okay, only for you and me to understand and visualize it like a tree. You see, they are giving us a drawing here, but if I submit it, it will fail for some test cases. Now, if any failed test case, they are giving you any input, this is how you need to imagine it yourself. Okay, and tell me the pre-order traversal for 1, 2, 3 is a pre-order. I hope you all remember. Okay, first we need to access the root node. What is the root node? The root node is 1. So first 1, then left node, left is not there, then right node, right again, root node, left node, right node. So 1, 2, 3 only you will get. Okay, now see, it's very easy, very easy. This is one of my favorites actually while writing the code after basic recursion. If root is equal to null, if root is, sorry, this is Python, root is equal to none, or if root is not equal to none, we have to go with again I need to call the same function again. So self dot pre-order traversal, okay, of, what is the order for pre-order? Can anyone post it in the chat box? Pre-order, what is the order for pre-order traversal? Is it left right root, or is it left root right, or root left right? Root left right. Okay, so first we need to take the root node. I have to return it as a listener. So what should I do? Maybe I'll take an answer outside of it. You see, this is our result. Here I'll go with result dot append of okay, root dot value. First root, then I have to traverse to the left subtree, root dot left. Okay guys, pre-order guys, first root, then left, then right. Okay, copy it, paste it. You see, I'll make it as right. Done. So if this is none, this is how it will be. Return the pre-order traversal of its nodes. No, how can we do that? I'm just doing some visualization in my head, that's all. We got 2 more messages. Very good. Root left right, root left right. You can use the meeting chat box. Now how to return? If I write return result here, let's see, let's run it. We'll get an error, I'm pretty sure about it. Yeah, result is not defined. Self dot result, if you are accessing I need to pass one more value if I have to return it as a list. Global res result is equal to empty. Let's try to do that. First one, 1 2 3, 1 2 3 1 2 I got again. What should we do? The problem is to return it as a list. That's what I'm trying to figure out here. Okay. Maybe we'll write one more function in it. We'll if root equal to none, we will maybe we'll just write a return. Otherwise we will try to go with this part. Okay. We'll do one thing. We'll make it a bit easy. Global etc and all will be a bit too much for you. So first let me write another function here. So result is equal to, I'll go with empty. Okay. Now I'll create a function called pre-order. Okay. Pre-order will be fine. Pre-order of, I'll be taking a node. Okay. If node is equal to none, if node is equal to none, I'll just return it. Okay. Otherwise I'll go with result dot append of node dot value. Then we will go with pre-order of, okay, node dot left. Then we will go with pre-order of node dot right. That's it. And once we are done with everything, it will have everything in the result. We just need to call this function first. Pre-order of a root I have to pass. Then ultimately just return result. Okay. And this is it. This is I'm more comfortable with. So result equal to empty I have taken. And we are returning result. Before that, we are just calling this pre-order function that we have written. So this will be called. And this will keep on doing it. Whatever you have seen in that animation, the same thing is going to happen here. Let's run it. Hopefully we'll not have any issues. Then we will submit it. Then we can talk about the recursive part for this one. Okay. You see, submitted 100% it is. So just observe how easy it is, how clean it looks. They wanted us to return it as a list. That's why we are just writing these two. Otherwise we'll not even write any of them actually. Or you can even remove this return none. You can even keep these things inside as well. And I think that will be fine. By default it will return none anyway. Yeah. You can also optimize it later. That's up to you. You can optimize this later. Done. That's it. Completed. So see here, this is our pre-order traversal. Now if you are unable to understand what's happening, you can do some tracing. Okay. Yeah. I like fine. I don't remember any of these questions, so you should not even remember them. You have to go on the go. Okay, on the go, you need to visualize, you need to make some changes, so you should not by heart anything. Now you can visualize the same thing for the second sample input output. Maybe if you do that, you will be able to understand how things are working. Okay, let's say the first node I have given you is that is 1. Let me take some other color, maybe blue is fine. Yeah, we can write on both surfaces. So initially result is equal to a big empty list. Now root is equal to 1, that is I'm pointing to 1, so node is not equal to none, so result dot append of node dot value, so 1 is appended. After 1 appended, I have called one more version of it. I hope you all remember my recursion presentation. You will be able to get this small box here, dialog box. Once this is done, then we will come to the left part. So this is done, I'll go to the left. Now here again, I'll access the root, node dot value. So after 1, I have accessed 2. After that, again from this one, I am accessing the left. So again, the left value, that is 4. So I'll crash 4 here. 1, 2, 4 we got. Okay, you see 1, 2, 4. Done. Again, we'll go to the next part. And do we have any left? No, none. It will return back to it. So then it is going to execute the right part. Okay. This is gonna keep on performing. Okay, whatever you guys are able to do it with your own eyes and all. Earlier you are able to come up with the pre-order examples and all. This exactly does the same. Whatever you have visualized, that is the visualization of the recursion. Okay, whatever you have done, how you are able to come up with the answer, you are able to move your eyes left, right, etc. and all, right? That itself is the visualization of it. If you do it on paper, you will get it exactly the same. Okay, are we clear? Are we okay up to this part? Can we move on to the next one? Can we move on to the next one? Are we okay up to this part? Are we okay up to this part? Can we move on to the next one? Can we move on to the next one? Okay, now see, I'll do some magic now. I'll do some magic now. Okay, I'll copy this entire stuff. I'll paste it in post order now. I'll paste it here. Now post order, just to make it readable, I'll make the name as post order. That's it. Post, just to make it readable. You can even leave it as pre. There is no restriction. Post, I have made it. Right. So now in post order, can you tell me the order of how we are accessing everything? We need to call this function first, na, so that it will get started. You are starting from the root, it will go to left, right automatically. It will give you the entire traversal of it. Okay. Yeah. For post order, what is the order? Left, right, root. So you see here, first left, then right, then root. Right? So after left and right, place that root line. That's it, done. That's it, done. That is post order. Run it, submit it, complete it. Okay. Now can you tell me for in order? In order, what is the order of it? You see, I came to in order now. This is a new question. I am going to copy paste the same thing. I am going to copy paste the same thing. Okay. I'll just change the name as in. Okay, so that it's easy for us to learn. Can you tell me the order for in order? In order. In order. Yeah, left root, sorry, left root right. So you see this root value that I am accessing, access it in between left and right. That's it. That's in order. In order is also done. Run, submit, done. Done for the day. You see how easy it is? Submitted, completed. Just like that, 3 traversals have been completed for you. Just like that, 3 traversals have been completed to you. Okay. done with all three traversals. Understood this one? Three traversals are done, completed. In order is done, pre-order is done, post-order is done. In is done, pre is done, post is done. Any doubt? Any doubt up to this point? Any doubt up to this point? Right? Let's see some tree related questions and all. Okay, binary search tree. Yeah, we have binary search tree. Let me first give you the introduction of binary search tree. Okay. Now we call it BST. BST in the sense binary search tree it is. Now see here. What is a binary search tree? Just go through the content that we have here. What is a binary search tree? BST, binary search tree. A binary search tree is a tree in which all the nodes follow the below mentioned properties. Okay, means the root node that you have here is 40. On the left side of the root node, we have all the elements which are less than it. On the right side of the root node, we have all the elements which are greater than it. And order will be maintained everywhere. Left side of the root, we have all the elements that are less than it. Right root node, we have all the elements that are greater than it. Okay. So order will be maintained everywhere. Now, if you are visualizing everything as individual tree, for trees, I would like you to this part. I want you to become a Gajini. Okay. Do not read what you had previously, or what I literally mean is, I want you to forget about this ever existed. Okay. You didn't have any tree on the right part. Only just look at the part that you had here. Do not even bother about the right side. Imagine this is the only tree I have given you. Now again you need to do the same thing. You need to think about it as your left, you need to think about it as your root, then proceed again with the left, right, etc. and all. Okay, that order, that values, everything should be maintained, should be good. Yeah, I know there are some issues. Now it would be fine, I guess. Now it would be fine, I guess. Now, okay. Now it's okay, I guess. Now, coming to binary search tree, why do we use a binary search tree? Please go through it. Whenever we want to search for an element, if we place them in binary search tree, it will give us log n time complexity. You might think, sir, why log n? If I am telling you, if I want you to check whether 48 is present or not, you will check this with the root node. Is the root node equal to 48? No. Is 48 less than root node? No. If it is less than root node, it would be present on the left half. So we don't have it here. Is 48 greater than root node? Yes. Now again check with this one. Consider this as your individual tree. Okay. Okay. Now is 48 equal to 36? No. Is it less than 36? No. It is greater than. Again, same thing. So doesn't matter how many nodes you have, you will get the answer in log of n. We have seen this for binary search. Every time you are reducing the number of iterations by half. So that's how binary search tree will also work. That is the speciality of it. Okay. I hope everything is clear. You guys are able to hear me properly. Okay. This is okay. About binary search tree, what binary search tree does. Understood about binary search tree? What binary search tree does? Done. That's the definition of it. We have lot of trees actually. We have AVL trees, we have red black trees, we have B minus trees, etc. and all. Lots of variations are there. Just get started with a basic one. Okay, all of them are not needed, but moving forward slowly, you can learn one by one. Okay, also done. So that's it, that's fine. So that is about binary search tree. Now let's take some binary search tree. Let's do some searching in it. Okay, let's see if there are any easy questions. I'll make you do them. Difficulty level easy. Convert sorted array into binary. Find mode in binary search tree. Absolute difference. Search in binary search tree. You see 82% acceptance rate we have. This is good. So let's do this one. Okay. Let's do this one. Binary search tree. So what is the question we have here? 700 is the question number. Okay. So this is a binary search tree we are having. Now, if you observe, go through the question once. You are given the root node of a binary search tree. Binary search tree in the sense, you know that left side of it, you will be having values which are less than root. Right side of it, you will be having values which are greater than root. Okay. So now, find the node in the binary search tree that the value equal to value and return the subtree rooted with that node. If such a node does not exist, return null. Okay, simply if the value is present, you need to return its address. From there onwards, it will traverse through everything. You don't even have to do anything. If the value is not present, by default you will be giving null only. Okay, nothing else you will do. That's it, that's about it. You see here the same thing we have to do for here. Number of nodes will be from 1 to 5000. Node value can be from 1 to 10 power 7, and they have confirmed that this root they are giving, it is a binary search tree. You don't have to worry about it, and the value will be also in that range. Okay, so now let's come to the code part. Now what we will do is, now here you see, I'll make it very simple. Okay, when you actually get a good hang of recursion, you will just only think about one iteration. It's kind of like self-solving. It will keep on going through all the other iterations and all. It will give us the final answer. That's how simple generally recursion is. I'm able to visualize lot of steps. Okay, maybe if you imagine playing chess or so, we would be thinking 3, 4, 5, 6 steps ahead now. In that, like when you practice, you will be able to visualize all those steps. Same goes with recursion, or simply speaking, which logic do you think is implemented in chess? Okay, let's search it. You see, chess game code, core logic, is it recursion? We'll get a simple yes or no. Yes, that's how it is. Okay, if you're good at mathematics, if you're good at chess, if you're good at puzzle solving, if you're good at teaching, you'll be good at programming. All of these will help you. I'm good at all of them. So yeah, coming back, it will automatically solve everything. Okay, so just visualizing, you guys will be also able to do that part, so don't worry about it. Okay, so while I'm present on a node, okay, while it is not equal to null, what I want to do is, if the value that I am searching, the user has given me value, if the value is less than the, or if the value is equal to root dot value, okay, see here, if I'll just talk about it, I'll just write it. You see what is the value they are searching in the first one, that is 2. Okay, it's better if I go with that. Done. Value is equal to 2. Now they have given me root. Is root pointing to null? No. Okay, let me write it down as well here. Maybe you guys will be confused. If root not equal to none, is root equal to none? No, root is pointing to the node 4, okay, its address. Then if root is not equal to none, it will have dot value in it, it will have dot left in it, it will have dot right in it. So what I'll do is, if root is not equal to none, I'll check if root dot value is equal to the value that the user has entered. If both are equal, I just need to return root address. That's it. Perfect, fine. Okay. If it is not equal, let's say, consider this scenario, you need to keep on doing this for every single line of code, then you have to add the next line. This is what I generally do. Okay, this is how I generally think. You see, I'll explain this to myself. You see, Rajesh, we have value 2 here, root is pointing to this 2000 address or so, so it is not null. So while we'll get into it, root dot value is 4. 4 is not equal to 2. So this is not the case. Now where should I search? Should I search in the left side or should I search in the right side? Guys, you tell me. Should I search in the left side or should I search in the right side? Which side? Left or right? And state your reason as well. Why left? Why left? Why left? Why left? Okay. Just like I am asking you this question, I'll be asking this question to myself. You see, I'm giving 6.5, 7 hours of training from morning 9 o'clock to 4:30. Then after I'm taking 7 to 9. So this session. So my brain will not be functioning at full capacity every time. And in your exam, you see, after writing 2 hours of aptitude, verbal and all, you would get started with coding. Or let us say you are coding something from morning onwards, it's been 2, 3, 4 hours or so. You will not be that active, okay? Like you were in the first 5 minutes, you will not be that fresh. So time to time, we need to keep on reminding ourselves. We need to take a small break. We need to keep on reminding ourselves. We need to keep our brain active. So how we will be doing that? We need to ask ourselves these questions. We need to assure ourselves. We need to explain the same question and answer that we already know to ourselves. Okay. So that's what I'm trying to convey here. Now I'll go with, okay, if it is not equal, if I'll check if root dot value that I have, okay, if the value that I have is less than, maybe I'll write it in reverse order. This would be easy for us to read. If value is equal to root dot value, return root. If value is less than root dot value, where should I search? I have to search on the left root node. So how I'll be doing it is self dot search of BST. Here I'll call it again and I'm going to pass the left root node here. Okay, so root dot left. Done. That's it. If it is less than it, I'll pass the left. If it is not equal, if it is not less, then definitely it is greater than only. Then self dot search BST of root dot right. That's it. It will search on the right side. Okay. At any point, if you are able to come up with the root which consists the, it will be returned. If you did not get it, you will come out of the loop. And I hope you all remember, by default, a function will return none. Okay, you don't even have to write it. You can even leave it. So you might think, sir, why you are stopping the extension? Sir, what is going to happen? You see, as I tell, be a journey in recursion, in trees. You see, if value is less than it, search of BST of root dot left. Imagine I have only given you this part. Okay. And imagine this is some 3 or so. Here you have your 2 or so. Imagine in that manner. Okay. So this is again starting everything from scratch only. Again, I have called this function. So everything will again start from the scratch only. So same thing is going to happen. Okay. Even if I explain that or not, same thing is going to happen. It will keep on doing it. It will keep on following the template. It will solve it. It will give you the answer if you have. Recursion is self-solving. It will automatically check all possibilities. It will give you the final answer. That's the advantage of it. Now let's try to run it. Hopefully we don't get any syntax errors. Okay. Yeah, we got one. Required positional argument value is missing. Yeah, we need to send the value as well. Comma val. Comma val. You see here we have 2 values now. So when we are calling the same function, we need to send it. So that's the syntax error. Now run it. It's taking a lot of time, maybe an infinite loop. Maybe an infinite loop. Yes, time limit exceeded. It's an infinite loop. Okay, I think we don't have to call it. Use this syntax. Now I'll do one thing. I'll update root. Root is equal to root dot left. We don't even have to write that. Root is equal to root dot right. Okay, just simply updating root value. If root is not equal to none, then it will check if the value is equal to it. In that manner it will keep on doing it. Run it, that's fine. Submit it, that will be also done. Searching in a binary search tree, 100% time complexity it is. That's it. This is the code for it. Okay, just go through this code for a minute, then let me know if you have any doubts in it. No, if the right node is greater than or if it is right node will be greater than only, no. Okay, you are telling me this manner, na. This is what I was conveying. You are telling me, sir, what if this is 13? Is that right, Yamini? Is this right? This is what you are trying to tell? Yes. So they have clearly mentioned it is going to be a binary search tree. They are going to follow that order. Okay. Root is a binary search tree. Binary search tree means you will not have it in that manner. Okay. This is how we store everything. So in order to come and be placed at this position, it has to pass 3. Okay. So it has to pass the root. First it will check while inserting. So root is 4, the value is 3, so you have to insert it to the left subtree. Left I already have 2, so I have 2 here. This 3 is greater than it, so it will be inserted on the right side part. So this does not work. A valid binary search tree will never have that scenario that you are mentioning. Okay, this is how it will be. The root node will be the highest value that will be present in the entire left subtree. Okay, and the root node that we have will be the least value in the entire right subtree. That's how it will be done. That's it. So I hope you guys have gone through this one. You want me to explain anything again here? See how simple it looks like. If you guys can visualize recursion, trees, etc. and all will become easy. But they are not easy when you actually go through a good level questions. You have to do a lot of brainstorming. Yeah, this is okay. This is okay. Can we move forward with the next one? Hey guys, can you please post that attendance link? Keep on posting it every 5 minutes. Whoever has that same Google form link, just keep on posting it. Fed up with everyone asking attendance link. It's not even 8:30. What will you do with attendance? Okay. So that's about this question. That's about this question. 700 is done. Let us try to come up with one more question. One more question. Let's go with high acceptance rate ones. To greater some range sum of BST, balance a binary search tree. Yes, this would be easy. Okay, constructing is not okay. Let's do this one. See guys, we have this question here. You can also open this in your lead code and check it out. Okay, I'll not say anything related to this, and I'll be giving you some 5 or 4 minutes, or maybe 5 minutes. Let's give you 5 minutes. Okay, I'll explain the question. You see, I'm starting the timer as well. Given the root of a binary search tree, it's a BST. Rearrange the tree in order. Okay, in order. We don't have to return anything. Oh no, then we cannot do this. Rearrange it in order. Actually we can, but that would become too complex for some of you. Let's see if there is any similar questions. No similar questions as well. Fine, so this is okay. We'll go with normal trees now. So binary search tree, have seen the searching, that is fine for me. Let's go with normal trees. Binary tree. Let's go with binary tree. Now coming to binary tree, we have seen the traversals. Let's go with acceptance rate. Let's go depth, height, etc. and all. Okay. Yeah, maximum depth, minimum depth. Maximum depth 77. Let's do maximum depth first. Okay. See this one. I'll increase the size of the screen. Yeah, I'll give you 5 minutes. I'll explain the question. Given the root of the binary tree, return the maximum depth. Maximum depth in the sense how long it can be, how long the chain can be starting from a root node. If you explore all the parts here, and this is only for description, we don't have to deal with any of this. We have to imagine it like a tree. Means they cannot give you everything in a detailed manner. Na? This is 2000, this is the root node. Okay, the value inside root node is 3. Left root node, left node of it is 9. This address is 4000 or so. They cannot give you in this manner, so they are just giving you as an array. I hope you get the point there. Done. So what is the maximum depth? Maximum depth in the sense, you see, 1 and 2. Okay, so the maximum depth is how many nodes you have? 1, 2 and 3. Include the root node, you have 3. That is the maximum depth. Okay, even if you go to the left direction, that's the maximum depth. From the root they are asking. It's not like from 9 to 7. From the root. Okay, the longest path from root node down to the leaf node. Right? That's the maximum depth. So think about it. See how we can do this one. How we can do this one. You have 3 more minutes. Think about it. How we can do this one. How we can do this one. Any ideas, any suggestions? Any ideas? You have 2 more minutes. Okay, left child's value might be less than right child's value. No, this is just normal binary tree. This is not binary search tree. Binary search is specialized for searching. Okay, we design it for optimizing searching. Okay, for example, whenever I am searching for something, now you have seen it. So let's see how Google search is so fast. Which data structure we use? Which data structure it uses? Okay, let's search for that. Binary search tree is specialized for searching actually. So AI is thinking it will give us the answer. My internet connection is unstable again. Is it binary search tree also? Let's ask it in this manner. I know it's BST, but things will be complicated, not that much easy. You see, binary search or binary search tree. Yeah, kind of like we give that as an example, but yeah, binary search tree is specialized for searching. Now you see our timer is done, so let's go through it. Okay, this is just a normal binary tree. We have maximum two nodes which are connected. That's what we have as a binary tree. So done. Now see here. Yeah, let's see. Very good, very good. We are getting some answers. Max of depth of root node. Yes, something like that, something like that. Let me tell you. Now what we have to do is, we'll also do the tracing for it, don't worry. So what we have to do is, if root is not equal to none, okay, if root is not equal to none, then left is equal to self dot max depth of, okay, max depth of root dot left plus 1. Otherwise right is equal to self dot max depth of, okay, root dot right plus 1 for right. Okay, now if root equal to none, we have to return 0. Otherwise we can do this part, left part, right part. Then what we can do is, we can return max of left comma right. Okay, I think we are done with it. So what I did was, I did lot of visualization. Okay, maybe you guys are only able to think up to this part, since I have lot of years of experience and lot of teaching experience. What I just did now is, I don't remember any answers. I don't by heart. I don't even study any of this. I've studied it long back. Only one time read. That's it. That's what I believe. If you learn it one time properly, then that's the actual way of learning. If you are present at this particular node, I came all the way, okay, up to 4-5 iterations or so, etc. Okay, and from the last onwards, I have figured out the output. I was able to visualize up to last part. How you will be able to do that? Through proper practice, okay, through solving more questions, okay, through visualizing. Write everything on a piece of paper, okay, visualize, draw everything in this manner, right? That will help you to understand it better. Now let's run this now. Let me check it out. If I'm confident about it, then I'll see. If there are any errors, we'll talk about it. This is fine. Now submit it. You see, done. This is also done. Okay, completed. Just a second. Yeah. Now, sir, how we are able to somewhere, and I'll be using it for you. You see, whenever you're unable to understand anything from the first session itself, I was telling you, do trace it. Okay, if you trace it, you will be able to get that. If root is equal to none, just return 0. Otherwise, left is equal to, I'll just call it as max depth, same function, max depth of root dot left plus 1, otherwise right equal to, like, along with that, not otherwise, max depth of root dot right plus 1. Okay, then we have to return max of left comma right. Okay, you see, I call these as tracing sheets. Let me show you what I mean by that. I constantly invent new ways of teaching and all. Okay, even for smaller questions as well, I think I have never mentioned it that much. We have been just doing the tracing normally. Even for smaller questions as well, or any code, if you are unable to understand it, you can prepare yourself a tracing sheet. Now, what is meant by a tracing sheet? Where is this? Yeah, last one, I think it is. You can just have your notebook rotated into landscape. Okay, write the code on top left corner. Do it for 5-6 iterations. If you do it for 5-6 iterations, take the input, note down the values at every single iteration. If you are able to visualize at every single iteration, if you are able to visualize what are the updated values, doesn't matter what question it is. If you are able to do that, you will understand why you are writing each and every line of code, or what is actually going wrong, or the presentations that you're seeing is nothing but tracing only. Instead of me doing all this work manually, I'm just showing them visually to you. Okay, and you're able to understand better. So that's the main thing here. It is helping you. Done. And people are here again to just mark their attendance. Let me just keep it. Okay, see, attendance link is the same. You can just fill the previous day's attendance and you can leave the class, so no issues there, right? That's it. This is about tracing sheet. So whenever you are facing any issues with any question, I would suggest you to do some tracing. Now let's close this one. Now maybe where is the question there? We need to take our tree as well. For this one, let's do that depth search. So where do we have here? I'll take the root node. Root node is 3. Next node is 9. Next node is 20. Next node is 15. Next node is 7. And I'll add one more node. I'll add one more node here. Okay. I'll make it as some 4 or so. Okay, leave it. So the maximum depth of this is going to be 4. 1, 2, 3, 4. It's not going to be 3. I wanted to add it. That's fine. Okay, that's my twist, right? So now see here. Now if you do the tracing part for it, now in the first iteration, the root is pointing to 3. It is not equal to none. So left of it, you see, for the 3, for the third root node, this is where I am writing it. For the 3, for the left, we are calling it again. So left is equal to, we are calling this function again. So imagine this is our, okay, entire tree they have given. This is the root node, right? Is root is none? No. For this also it will be called again. You see, left is equal to, let's say I'll call it as max depth of, what do we call it? Okay, max depth of 9. This has created one more function call. Okay, 9 we have, is 9 equal to none? 9 not equal to none. Okay, so if will not be returned, it will come to left. Left is equal to max depth of root dot left. Do we have any left? No. So left is equal to 1. Okay, so root dot left, if you write, what you will be getting? 0 na? So 0 plus 1, that's what. Now this line is completed. Now the next line, right equal to max depth of root dot right plus 1. If I search root dot right, you see root dot right is none. So for that function, you see, for this left function will be called. That left function where root is none, none equal to none you will have. So that will return back with 0. Okay. For the right function, again you are calling it. Now what is the right value here? None. So for that none also you will again get back 0. So root is equal to, right is equal to 0 plus 1. Now you see this level, how many nodes we had? 1 only. Left and right are not there. So left and right is equal to 1. So max of left and right you will be getting 1. So from the left node, we will get 1. Okay, you see now I'll erase all this messy diagram here. All this I'll just remove it. Okay. Done. Now for this right one, what we got was, we got the return as 1. So left equal to 1 for it. Okay, for the root node, if you go through the entire left subtree, you are getting only 1. That's it. Okay. Now right subtree is equal to, again, depth of the right part. So root dot right, that is 20. Okay. Now for this one, imagine you are only given 20, 15, 4 and 7. This is the root part. Again, for this you will be calling it separately again. Okay. So imagine 15 and 4 are the only ones. Sorry, I got disconnected. Yeah, hopefully we'll be able to have the previous. No, we don't have it. Yeah, fine. I'll try to draw it in maybe this time. Okay, going to be interesting. So if you know this one, you will also get the minimum. Is 837 or so. Na? So we will continue with it. So just a quick check. Audible and visible, right? Just a quick check. Audible and visible. Just a quick. Okay, audio settings and all are fine. Internet. Yeah, internet is fine. Just a quick check. Let me change this setting group chat. Yeah. Now audible and visible. Done. So let's use paint for this time. So maybe that visualization will be better with paint. Let me open paint. I've copied the entire text there. Let me paste it here. That's it. That's what we have as of now. Right now you see, no, you cannot edit it again. No? Yeah, we have enough time, so we'll this one properly, then we can move on with the next questions actually. are at this time, and maybe tab will not work here. Yeah, I'll try to push as much as possible inside. Yeah, have some internet issues. Right, so we are drawing this actually in Paint, so that's what we have been doing. Now let's just connect them normally. Let's not this one. Let's go with the brush that we have here. Okay. Let's connect this one, this one, this one. Okay. 0, 3, 9, 20, 15, 7, and this is our 4. Let's think about it in that way. Okay. Now, when I am actually calling this function for the first time, what is the root value? Root value is pointing to 3. Okay. A root is present here. Now, root is equal to none? No, root is not equal to none. Then what will happen? It will call the left value. Left is equal to again the same function with the root dot left as its root node. Okay, so imagine taking out this part. This is going to be our root node. So we have seen it. So this again it will go to right. Both of its left and right are going to be null, so they will be returning 0. This is 0, 0. That's what we'll get here. Okay. Now its left value is 0 plus 1, right value is 0 plus 1. The maximum depth up to this point is 1. That's what it will be returning back to the original root node. That's what we have seen. So root dot left plus 1 we will get. Root dot left is 1 returned. So 1 plus 1. For the original root node, the left part is 1. Up to here it is. Now we need to do the right part. Right part again, you see, right part, what are you giving? Right part, you're coming up with that 20 there. So if I take out, yeah, that part a little bit more. Okay, imagine having okay, it is free form. Yeah, imagine having all these parts selected, copy it, paste it here. Okay, for this one they are asking you for the left and right nodes again. Okay, we got the right node. For this one again you have to go with left node and right node. So for that, how the recursion will be is not getting. You see, this is the root node. Okay, this is the root node. Again, root node is not equal to none. If it is equal to none, you will return 0. For this, you will first go to left. Okay, for left again it will be called. So you can imagine this as a separate one. Okay, if you want, imagine this particular piece as a separate one. Okay, imagine this particular piece as a separate one. Okay, for this is the root node for it. This itself is equal equal to none? No, root is not equal to none, it's pointing to 15. Again, you will be calling left. What is that left? Left is going to be, okay, pointing to 4. Again, that will become another recursive call. You can imagine that single 4 as another recursive call. This is the root, okay. Root is not equal to none. If you will again call the left value is none, so we will not have anything. We will be having 1 returned. Right, we don't have anything, null. So left and right are returned with zeros. That is +1 we are doing now, okay, including this one. So max of 1 and 1, you will be getting 1 only. For this, you will get 1, okay. When it comes back to the previous iteration, it will go with 1 plus 1 again, okay, because of this particular values that we have. Let me just try and point it out. It's becoming messy, okay. You see, we are using left dot max of max depth of root plus 1, right? So when it comes back again to the previous one, it is going to bring that 1 with it. You see, when you called this particular function, it is going to bring that value back to you, okay. So we have 1 plus we have 1. Now for this one, actually it had 0 and 0. It brings back 0 actually. So this one was 0 plus 1. So in that manner, this tree will keep on iterating. This recursive tree will keep on executing all the calls recursively, okay. It will give you the count each and every node at present at each and every level, okay. So what happens here is, here it is 0, here it is 0, okay. When you come back, 0 plus 1, 0 plus 1. So what is maximum of 1 and 1? That is 1 only. When you come back, 1 will be added with 1, means this particular 20 value is added. Here also we have 0, 0, nothing. So comes back, this value is 1, Even if you go left or even if you go right, maximum depth is 1 from here. You will come back to this one, carry that 1 value. So we have 1 and 1, again 1 plus 1, 1 plus 1. So maximum depth from here to left and right is 2 only. You will come back, okay. This is carrying the max value 2. So 2 along with this particular node 1. The right subtree value is 3. Now the left subtree value you have already seen, 2. Bigger, 2 or 3, max of left comma right, that is you will be given 3. So this process will keep on executing, this process will keep on iterating. Or let me show you one good platform where I can show you this. Visual Algo we have a platform where you can visualize algorithms. Visualalgo.net. If you come here, you will be able to see a lot of algorithms, you can visualize them. And the particular thing that we are looking for is binary tree. Where is tree? Binary search tree we have, binary heap we have, yeah, max depth in visualization. Visual Algo will type. You're not getting it here. Maybe if we can substitute the code, that might be one of the cases. Let's try to do that substitution maybe. Custom code. Yeah, maybe a root it will not recognize, but that's fine. Custom code, we could have entered everything. Let's see if this works out, that's okay. Otherwise, fine, not an issue. Okay, we have to even enter the input value. No, this will not work for it. Yeah, you can check out this site. This is generally good actually. So binary tree, you're not giving anything. We don't have anything. Yeah, try to do it on a piece of paper, that will be best. So this is also a bit better if you can get it, or images also. They have sometimes presentations like mine. If we have that, that would be easy. No. Leave it. So yes, do some visualization. Take a big piece of paper, try to trace it, do the tracing recursion just like I did. You will be able to figure it out. Okay, this is maximum depth of binary tree. Now the opposite of it, we have minimum depth of binary tree as well. Okay, you see, minimum depth of binary tree. Let me copy this particular piece of code and I'll paste it here. Minimum depth of binary tree. Now, what do you think we can do in order to get the minimum depth of binary tree? What changes can we do to the maximum depth in order to get the minimum depth? Okay. I'll see, I'll just bring the code, I'll paste it here. I'll just keep everything the same. I'll just make that max depth to min depth. What do you think? What else we can change to get the minimum depth? Minimum depth. How can we get the minimum depth? How can we get the minimum depth? How can we get the minimum depth? Any idea? And again, my internet connection is unstable. Any idea? How can we get the minimum depth? How can we get the minimum depth? Well, guys, hope I'm still audible. You guys don't have chat access or what? Yeah, okay, you guys have chat access. So, what happened? Hello, hello, hello. 1, 2, 3. I'm audible? Yeah, done. What do you think we can modify to get minimum depth? It's not like this max function to min function. It will not work in that manner. That's different. That's different. What can we do to get minimum depth? Any changes you would suggest? Anything that you are able to visualize or draw on a piece of paper? Right, then I'm not getting any response from your side. Okay, so go through it, try out minimum depth, take it as an assignment. Okay, well, solve it the first thing tomorrow. With by then you will be able to visualize that maximum depth as well. Okay, go through maximum depth, try and visualize it, and try to solve minimum depth here. Tomorrow we'll talk about minimum depth, and I hope you remember tomorrow is the last day of the training. We will be going through graphs. I'll give you a good idea about depth first search, breadth first search, terminology that we use in graph, and we will go through some programs on it. Okay, lead code questions only. Some programs, beginner friendly, which will give you a good idea about graph. Creation and all will not be there. We already have a graph, we will be accessing it. Okay. That's it from my side. So 5 more minutes are there. Do you have any queries? Do you have any queries? Any questions that you want to ask about today's session or any of the previous sessions? Do you have any queries? Do you have any queries? Have any queries? Try to visualize that. Okay, depth, maximum depth. Recursion and these trees, etc., and all, you need to visualize everything. That will make it easy for you. Do it on a piece of paper, you will be able to find it, so not a problem. Done. That's it for today. Then I'll see you tomorrow. Bye bye.